Hey everyone, so I thought it would be nice to show you how I make capacitive power supplies. I use these in all sorts of projects. I've got a momentary switch which works on a flip-flop circuit, which turns my lights on, and that I'll just use one of these to power the circuit board on that. I've had it running for about 3 years now, so I know that these work pretty well. They're found in all sorts of things these days, from boiler PCBs to wireless room stats, loads of things that require small power consumption that are quite small. They use these in them. I won't go through the dangers with you too much. If you're looking at these, you obviously know the dangers of transformerless power supplies. They're line voltage. There's nothing separating the output side from the input side, but let's go through that and have a look anyway. Right, so the first thing I do is I want to figure out the total load of this circuit. How I do that, this one's simply going to do a relay and a white LED, and step down at 12 volts using a Zener diode. So what we're going to do is the LED is equal to 20 milliamps. The relay is equal to 20 milliamps. And then just from messing about with these in the past, I've found out that really you need to allow a tolerance of about 10 milliamps, because if you design it like perfectly, it just doesn't work, just because there's losses within the circuit in other areas. So our total current that we want to be able to draw is going to be 50 milliamps. So we'll design it to 50 milliamps. More likely we'll probably get a little bit less, maybe a bit more. It depends if we get the values to match perfectly or not. So we want 50 milliamps. Okay, so we know we want 50 milliamps. The next thing we're going to do is find out the value of C1, and to do this we do, brain fart, hang on, to do this what we do is we go your supply voltage, which is 230, and you divide that by 50 milliamps. So we're going to go 230 divided by 50 milliamps gives you 4,600 ohms. So if we were to do this with a resistor, we'd use 4,600 ohms at some ridiculous power value, because it's going to burn the moon into a million billion moons. So the next thing we need to do is we need to transform this value into a capacitor value, and to do that we use this formula, which is 1 divided by, close bracket, 2 times pi times the frequency of the supply, which is in England it's 50 hertz, times the resistor value that you've just worked out. So let's plug these in. 1 divided by, close bracket, 2 times pi times 50 times 4,600 equals, we're going to times that by, so that's going to give you let's do equals 0.69 microfarads. So that's telling us now that to get the equivalent of 4,600 ohms in capacitive reactance, we need a capacitor value of 0.69 microfarads, or something as close as possible. Okay, so we've restricted this side of, well, anywhere past this capacitor to 50 milliamps, but we're still dealing with high voltage even after it's rectified. Obviously it's not smoothed yet. That's something else. But just to explain a little bit about the primary side, I probably should have done this first really. fuse it down. There's 500 milliamps. That's way too much, really. You don't really need that much, but there is a slight inrush current. So if you use something smaller and it was a quick blow fuse, it'd probably go. But 500 milliamps, you know, if something went catastrophically wrong, it would kick in. Yes, 100k across the C1, which we now know is going to be 0.69 microfarads, rated at double the incoming voltage, so let's just say 400 volts. That capacitor is just a bleed capacitor, so if there's any voltage left on that, a discharge through that capacitor. And then there's just a 1 mega ohm just to take out any spikes or anything on the line incoming. And then, so that's that side dealt with. We come to the bridge rectifier side. Even after this has been rectified, forget about this side of the circuit for a minute. We'll leave that alone. This, if we were to measure voltage across here, even though it's restricted to 50 milliamps, it's still going to be very high voltage. The other thing which is good to know about these circuits is the load is related to the voltage, in a sense that what I mean by that is, if you had no load on this side, this voltage would be equal to the line voltage. What's even scarier is if you had a capacitor here, mains will come in, this side is completely gone, it works as like a buffer. The voltage will just build up to the peak, sorry, not peak, just to the peak line voltage, which in the UK is 340 volts. If you've got a capacitor here, which normally you just rate at the you know, double the voltage of what you're aiming to achieve, it's just going to keep going until it starts leaking current back enough to regulate you know, the 12 volts which you want. So if you just stuck let's just say 470 microfarad capacitor at 200 volts on this, if you just left it and just charge it, that capacitor will charge up to 300 volts, nearly 300, well, it would probably reach 340 volts, because it's a load sensitive. So these circuits require a load at them all the time. There has to be a load at them. For an example, if we want 12 volts at 40 milliamps, well, we're doing it for 50, you know, for 50, but let's just say 40. So we want 12 volts, we want that at 40 milliamps is really what we're after. You know, we've designed the capacitor and everything for 50 millivolts, but we actually just want 40. If you do 12 divided by 0.040, that will give you 300 ohms. So to get 12 volts out of this circuit, there has to be at least 300 ohms load of this. Without that load, this will reach peak voltage. Okay, now to find the value for the Zener diode, normally you would just do the what is it? It's the voltage in, take away the voltage you require, and then you divide that by the current. So say normally you would go, if it was a 18 volt supply, 18, and then you wanted 12 volt, you get 6 volts, and you do 6 divided by your current, and it'll give you 150 ohms. So normally you whack 150 ohm resistor there, and that would limit it to you know, 40 milliamps. But because we've already designed this to work for 40 milliamps, we don't really need this resistor, but it's good practice to put it in. So a very low resistor is required. You could leave it out, but it's good practice to leave it in. So just for argument's sake, we're just going to do this as 100 ohms, which it will cause a slight imbalance. So on this here, we're going to see just a bit more voltage than 12 volts. We might see around 15 volts here and 12 volts here. With regards to this capacitor, you're just going to be, it's just a smoothing capacitor, so the bigger the better really. Not too much, because otherwise it takes up too much current, but you know, 1,000 microfarad would do the job, and then we want it at least double that voltage, as long as there's a load. So let's just say 25 volt. The bigger the voltage the better really, because under a fault condition, you know, that voltage shoots up, it just explodes. And then again, we've got this, you know, this is just a fairly standard. We've now regulated it at 12 volts for the Zener diode. This here, we're just going to whack a 1k in. Actually, no, we won't. We'll do a 470 ohm for that one, and that will allow enough current for that, which is going to be about 3.2 volts. And then the relay just works. You know, that's just going to pull off 20 milliamps from the positive to the negative. So that's basically it really. I mean, that's how I design capacitive power supplies. We'll have a look at one that I've made, and we'll do a few tests on it. So this is the circuit. This is one that I've made earlier. We've got live from the mains, neutral. I always use a isolated power supply. That's limited at 500 milliamps, and if I just went to touch a live or a neutral, I wouldn't get a shock because it's isolated from the mains. I mess around with a lot of mains electrics, so that's why I've done that. So here we've got live incoming. We've got the 1 mega ohm resistor going down to the neutral, and then we've got a 100k in parallel with a 68 microfarad 400 volt capacitor, sorry, 0.68 microfarad bridge rectifier. On the other side of the bridge rectifier, we've got the 1000 volt electrolytic capacitor, and then that goes on over to the next side. I don't know if you can see this, and that goes to the Zener diode, 100 ohms Zener diode to the output, which is the 470 ohm resistor, the LED, and where's that bloody relay gone? And a relay. Oh, there's a shed door opening. So I'll just show you this working. This is the main supply. The relay's kicked in, and the LED's on, as you can see. Let's do a couple of tests. If you can see this next to it, maybe. Is that pushing it a bit? Can we zoom out? Cool, okay. That's mains voltage, but like I said, it's isolated, so even if I touch the live, I won't get a shock. Right, let's do mains voltage test. So this is your incoming AC voltage, which is 200 and, just round it up, 230 volts. Your output voltage on the bridge rectifier, DC, 16 volts. And then on the, move my hand, Zener diode, 12 volts, LED, 3 volts, and there's obviously 12 volts on the relay because the relay's kicked in if it's going to stay up there. Let's chuck a capacitor under there to wedge it. So let's do a couple of other thmillions. Let's see how much current maxed out this will actually draw. So I'll just change this to milliamps. I'll turn the mains off for this bit. So what I'm going to do is I'm going to short out, basically I'm going to short out the Zener diode and see how much current we can draw from this circuit maximum. Actually, yeah, I'll do that. $41 milliamps. I just don't care, do I? 41 milliamps. Let's see what it draws from the main side. So we'll change that to AC. The whole thing draws 44.5 milliamps. That's pretty good, you know. That's we designed it to draw 50. Okay, what I'm going to demonstrate now is I'm going to try and show you what I mean earlier about the stray voltage. So we know this works. This works, you know, perfectly well because there's a load on the other side. Now, if I take the loads out, including the, well, if I just take the Zener diode out, that leaves the capacitor is the only thing that's in circuit. Everything else now isn't in circuit. I don't know if you can see this, so it's not a very good camera. And we're going to measure the voltage on this capacitor very, very briefly. Let me put these on first. Straight away, 36 volts straight away. Oh, my hand was in the way. Hang on. Don't want it to blow up in my face. It's still at 25 volts, and you know the circuit's not even turned on. Okay. That's on now, 35 volts straight away. So the reason that's going up to 35 volts and stopping is because it's you know, the current's coming across the dielectric inside, so that's reducing it. But eventually that's just going to pop. You know, if we get another capacitor, so maybe something that's a bit larger, like this one, which is a 400 volt, 100 microfarads, it will charge this capacitor up to over 300 volts, or nearly 300 volts. Let's do that now. So power's on. That's charging this capacitor up now. $313 volts, and it's creeping up. Can you see that? So that's what I mean about it being a load sensitive circuit. That's the other thing that's quite dangerous about this. Boom. So it always has to have a load on. You can't switch a load out of these circuits. The other way to test it is earlier on. I can't remember if I showed this, but we did 12 divided by 0.040. That's 300 ohms. So if I get a 300 ohm resistor and I place it across the bridge rectifier on the DC side, it should come up with around 12 volts. This is actually just a 220 and a 100 ohm resistor in series with each other, because I didn't have a 300 ohm. So if we put that there, if we turn this on and measure the voltage on the outside of that. 13 volts. So the other way you could use this is have just a very, very small load and this on all the time. So you could probably just run this LED, switch the LED in and out of the circuit as long as there's a constant load on it, and that'd be fine. That's the only way you could use this circuit, by switching the load rather than the incoming supply. So there we go, that's how I make capacitive power supplies. Few things to remember is obviously the line voltage isn't isolated from this side, so that can be quite dangerous. Working out this to get this value as close as possible is pretty important. The stray value on this, absolutely, probably the most important thing about this is making sure you've got the right capacitor to handle the voltage if something was to go wrong here, or make sure that you've got a constant load on this side to balance the current in the circuit properly, so it's drawing the right amount of current to what you've designed the circuit for. I'm not sure I've been very clear on this at all. Comment and let me know what you think, and if there's anything else I can go over to make it clear, or maybe I'll just make another video once you've all looked at it and gone, ah, it's rubbish, this doesn't make any sense. I can make another video and let me know what you think. Thanks, bye.